So I'm mostly going to tell you about a technical program for trying to achieve something fairly ambitious, which I don't think there's enough of these days. And that is to design AI systems that will be both powerful and safe, with safety not just something we hope, but something we have as much guarantee about as possible. And I'm creating an organization, a nonprofit that will be working on this thing, and I've started recruiting people for that. So mostly right now recruiting on the technical side of things, research scientists and research engineers. So if you're interested, reach out to me at any moment. All right, so I'm going to start with a bit of motivation. We are on a path to build AGI, potentially, superhuman. It's very likely that if we reach the AGI level, the human level, it'll go superhuman, at least in some directions, for a number of reasons. And that could be, exciting and probably has a lot of economic value, but also a lot of risks. One way to understand why there are risks is simply that the kind of AI agents that people are trying to build are can be applied to good goals or malicious goals. And it's also possible that the goals themselves are coming from the AI itself. So how could that be? Well, one simple way to understand that, at least the way I picture things, is if a dominant goal for the AI is self-preservation. And self-preservation could come out as a side effect of other goals, or as I'll explain, if the AI is trying to maximize a reward and takes control of the reward mechanism. So if that happens, if we have self-preserving AIs, then it'll be, and they're smarter than us, then we might be, in a very bad position, and the AI would resist to be turned off, and would try to make sure we can't ever turn it off, right? So I don't understand why, so few people in the world currently don't worry about this, but I do. We don't know how to fix this problem at a scientific level, and we don't know how to fix this problem at the political level. How do we make sure humans around the planet don't do the mistakes of building a machine that could destroy us all? There is, of course, quite a bit of work in AI safety already. I think it's completely insufficient compared to the importance of the task. But I find the current work in general not reassuring, not sufficiently reassuring. So if you think about evaluations, they're typically, as far as I know, just spot checks. We can make them better with automating some of that, like with automated red teaming. Trying to evaluate what the capabilities are is also hard with the current deep learning state-of-the-art. Automated interpretability is interesting, but I don't feel we can get the sort of assurances that we'll find something bad if something bad is cooking, and I'll give you some arguments for that. So I think we should diversify our exploration of ways to solve this safety problem and be ambitious, so that it's not just something that's going to help us to make sure the next generation of LLMs will not insult anybody, but actually protect us when we reach the AGI level. Yeah, one reason why we could end up having a self-preserving AI is simply that some humans will want that to happen. If your value system puts intelligence at the top, then if they are superhuman AIs, then you might want them to be self-preserving and fend for themselves, And I think that is a very dangerous proposition because we don't know if even these entities will be moral in the sense that we think of morality. Even if they're self-preserving and smarter than us, doesn't mean that they have the same value system as we do, even if we try to make them this way. So yeah, there are many ways in which we can end up with a dangerous AGI. Some people tell me, yeah, but well, it's just something in the computer. Who cares, in the real world? But of course, if you think a little bit more, it's very obvious that our world is heavily digitized. People can be influenced. Criminals will do things for money. It might become difficult to stop an AI once it has copied itself in many places on the internet, and so on. And the day that it can control robots or design robots better than those we have today, that are strong enough to basically do the manual work that we do, then it doesn't need human anymore. And then, that doesn't bode well for us. Okay, let me tell you about one of the scenarios for things going wrong that I find the most concerning. So it's the scenario of an AI taking control of its reward signal. It applies to AI agents that are trained with some form of reinforcement learning, where they're basically trying to maximize their reward, future rewards. Right? So I use the analogy of training animals to explain this. If you train a dog or a cat to not do something, like not go on the kitchen table, you might succeed by blaming it when it does it, but it's probably not going to be a perfect alignment. In particular, when you're not in the kitchen, they'll do whatever they want. So training an AI with rewards or a reward function is something that leaves a lot of room for a misalignment. Now, if it's just a cat or a dog, it doesn't matter too much. But what if it's a grizzly bear? It's an image, obviously, something more powerful than us. So first of all, even the question of how do we give the grizzly bear rewards is tricky, right? So we need to build a cage so that we can give it fish without it just grabbing the fish. But if it's powerful, in the case of an AI, it's smarter than us, it finds a way to hack the cage, right? And then it can just grab the fish from our hands. It doesn't need us anymore to get the fish. So in the case of the AI, if the AI takes control of the computer in which the rewards are recorded, as was explained by Michael Cohen, who's sitting here in some of his work, we would be in that kind of situation like the grizzly bear. The problem is we don't know how to build a cage that is going to be guaranteed safe. And since our intelligence is limited, if we don't do something like that, there might be, it's like, our cyber defenses. There's going to be some loophole somewhere, very likely, that a smarter AI could discover. But there's worse in this scenario. And again, I owe my discussions to Michael to understand these things. So one of the things that's very worrisome about this kind of scenario where the AI is taking control of its rewards is that we might not see it coming. So why is that? So first of all, the plan of escaping from the cage, plan of taking control of the reward, so that the AI can give itself maximum reward forever after that, is not going to work for the AI if we figure out that the AI is doing this, or wants to do this, or starts to do it, and then we just shut it off, right? So it needs to make sure that it's both going to take control of the reward and make sure we can't ever put it back in the cage or shut it off. Otherwise, it's not a good plan. Because there's another plan which it would do until it figures this out, which is just do the things that we want. That's going to give it a lot of rewards. And the smarter it gets, the better it's going to be at behaving well and apparently morally, right? Because it's going to learn more about what we expect. Until somehow it figures this escape plan. But such an escape plan will not even come to its mind, if I can say so, if it isn't safe enough from the point of view of the AI, right? That it has enough certainty that it can both escape and make sure we won't put it back in the cage or kill it. So this is kind of concerning. You could have a number of counter arguments. For example, well, what if you only use RL during training and then with some pre-trained reward function like we do right now with RLHF? But once it's deployed, it doesn't need reward. So why would that happen? What would it try to get control of something which doesn't exist anymore, doesn't matter anymore? And that's simply because how these neural nets work is to internalize the reward function, right? So when we train the neural net in AlphaGo, for example, once it's trained, it has internalized the reward function. In other words, it's going to come up with moves that try to maximize this reward function, even though it doesn't see rewards anymore. It doesn't need to see rewards. It has sort of amortized the job of optimizing the reward. So this is what neural nets do. The amortization means instead of doing the work at runtime, like trying to find a good plan, which is an optimization problem, you train an AI once and for all, and it sort of then will behave as if it was optimizing this reward function, right? And that's true for optimization of a reward, but that's true for sampling. So a lot of the work I've been doing is amortized sampling. You can train an AI. Like when we train a diffusion net, for example, as a generative model, we, instead of doing MCMC, which would be runtime very expensive, where you search for good samples, you just train the AI once and for all. You pay a big price, so that's the amortization, and then it's cheap. You just sample from the neural net, right? So that means the way that those plans are going to come to the mind of the AI is, if they're good according to the estimation of this implicit knowledge about the reward, if they're good, then the AI will have a tendency to play those things. And of course, it could also do runtime optimization in addition, like in AlphaGo. So you could be combining both things. Another argument that was given to me recently is that why would the AI do this bad thing of trying to take control of the reward if instead it could just do the things that we're instructing it to do? If we have a good model of the world and a good model of what people want, why would it not just do these things? And my answer is simply that it wouldn't get as much reward if it do the things that we're expecting, compared to just taking control of the reward mechanism. Why is that? Because if it takes control, it can put the value of the reward to whatever its maximum value is forever, right? Whereas if it does the things we want, it means it can't possibly always have the same maximum value. I mean, if the reward function was constant, it would be not very useful. Like in order for the reward function to contain information, we need to make sure that, well, sometimes the AI doesn't get as much reward, so that there's a signal there for things that are slightly wrong and could be improved. All right, so going back to what I said at the beginning, what I'm focusing on myself are two requirements that we have to get right in order to avoid AI catastrophes. The scientific question of how we build a safe AI that's really strongly safe, right? And I think this should be the biggest scientific project for humanity, because like rationally, like we shouldn't want to disappear. And the second thing is the coordination challenge or the political challenge. And how do we make sure that whatever safe protocol we come up with is going to be followed across the planet? Yeah, so you might ask, why do we need the first one if we get the second one right? And that is because the, regulations and treaties are not going to be 100% protection. Like somebody is going to cheat. Somebody in some country is not going to follow those rules. And we'll need a safe AI in order to protect us against the potentially rogue AI that could emerge. So yeah, so that's what this slide is saying. So how do we do this? So there are technical aspects, but there are also like governance aspects. If we're going to build a safe AGI, while we're doing this, how do we make sure we're not making things worse in terms of humanity's probability of survival? For example, we don't want to do something to train an AI that will be very powerful, smarter than us, and that we haven't really gotten the safety right. Also, we don't want the work, if it becomes more powerful than existing AIs, we don't want that to fall in the wrong hands. And the wrong hands could be, your own government. Could be simply that the code or the methods have been stolen by some organization which wants to exploit that for making profit or for military reasons. So the governance of, I think in general, the governance of frontier AI systems should be something we spend a lot of time on to make sure that the security is there, but also that it's a multi-stakeholder in the sense that no one person, no one organization, including no one government, can easily take over that project. So I think it has to be multilateral and involve multiple governments, maybe the UN. Ultimately, all the AGI projects should have that kind of governance. All right. So now let's go a little bit in the science side of things. For the last few years, I've been working on AI for science, machine learning that can help to do experiments and to come up with explanations for data in the way similar to how scientists do it. And in fact, if we continue on that path, we could eventually build AI systems that are not agents. In other words, they can't do anything in the world by themselves. The only thing they would do is come up with scientific theories that explain the data, just like what scientists who write papers do. And they wouldn't have any goal in the usual sense of AI agents. Their training objective would be just, find good explanations for the data and then tell us what these explanations are. So what is a good explanation? A good explanation is one that is compact, in fact, ideally representable in natural language, like something you put in a scientific paper. And of course, it has to be coherent with the data and coherent with itself. If it has multiple parts, usually, a theory has multiple parts, its parts have to be coherent with itself. So all of that can be put in a formal language of mathematics, of probability. And what you get is the Bayesian posterior over all the possible explanations, all the possible theories that explain the data you care about. So how do you do that efficiently is part of my research program, and that we've made some progress in the last few years. So we could do that. It would be immensely useful for humanity to have AIs that can help us, in medicine, in climate science, and many other things to help our science move forward in ways that help humanity. But it wouldn't be sufficient to build an AI agent that could protect us from a bad, dangerous rogue AI. But it's a recipe that we could use as part of building a safer AI, and that's what I'm going to be telling you about. Okay, but before I do that, a few more words about the AI scientists, or now I call it scientist AI, just to avoid the confusion. So I take a lot of inspiration. I have taken a lot of inspiration throughout my career in my work in AI from human intelligence, human cognition, neuroscience. And if we ask the question, how is, can we have an AI that will generate a theory of everything, just like all of the science that explains as well as possible everything we know? It seems a little bit daunting. And it's not the way that brains do it. The way brains do it is that we have this bottleneck of conscious processing through working memory, in which your conscious thoughts go through, and it's very few bits of information per second compared to the massive amount of information processing in your brain. And you can verbalize it. It's something that's interpretable, right? So no human ever puts out, here's my theory of everything, including, how to do all kinds of things and approximate things properly. Instead, we come up with little pieces at a time. So a lot of my research program is anchored in this vision. If you think about the way we write science, is all like that as well. Like we write a single paper with ideally like a single contribution main message. So everything about our theories of how the world works or explanations for things that have happened in data is broken down into small pieces that hopefully are going to be compatible with each other. Not always, because there are maybe multiple theories or multiple explanations for different parts of our knowledge. Right. So yes, so let me move to other aspects. The way that we're currently training neural nets is end-to-end, going from contexts like inputs, queries, documents, images, whatever, to other things that we observe in the data, like the next word, the next image, whatever. And that's basically supervised learning, to learn about how the world works. I mean, it isn't supervised because we just take the data, but we're using supervised objective in order to come up with a good model. But the model and the understanding of how things work and the ability to answer questions are mixed together in one neural net. And we can't disentangle the, what it is that the neural net understands about how things work in the world from how do I answer this particular question, which is inference, right? So there's like knowledge representation. How do things work in the world? That's what we usually call a model. And there is, how do I answer a particular question? Why are these things separate? Well, think about quantum physics. The model is very simple. It's a few equations. But as you know, answering questions is hard. It requires intractable computations in general, except if you have a very small system. So you see that the computation involved in doing inference is quite different from the computation or the representations involved in stating what you know. And in fact, in general, I don't have a theorem for this, but a very strong belief. In general, the number of bits of information you need to state your theories about how things work, or similar questions, is very, very small compared to how many bits of information you need to represent the computation to answer questions doing inference. As an example, think about AlphaGo again. What is the model? It's the rules of the game. It's one page, which can be put in code. Inference is a huge neural net that has compiled how to play in a way that is consistent with those rules. But the way we train LLMs, for example, doesn't have that separation between what the model thinks about how things work and how to answer questions. And what would be the advantage of having that separation is better generalization. Why is that? Because if because the inference is something, how to do the inference right, is something you could derive in principle through training and computation from the model. So again, if you think about quantum physics, in principle, you could learn how to answer questions by running a lot of simulations of your model. And you don't need any data for that. There's some caveats, but the principle is there, right? So how much data do you need? Well, you need only as much data as is sufficient to establish the model, which is going to be much smaller. And so the amount of data you need to achieve a certain capability to answer questions is much smaller if you have this model-based approach. By the way, all of science is based on this principle, right? Yes. So there are other advantages. For example, we may have lots of prior knowledge or inductive biases. Like causality is the one that I prefer. It's very general. It's an assumption about the world. Actually, physicists probably would say it's not true, but it's good enough. It really helps us a lot to view how the world works through the causal lens. And I could argue why you could get much better out of distribution generalization when you do that. Okay. There are other issues with the sort of end-to-end maximum likelihood approach that have to do with epistemic uncertainty. The way we train these neural nets, as you know, is that they can, you end up with the possibility of these predictions being wrong with high confidence. In other words, the neural net is sure that this is the right thing to do, but it's completely wrong. And if it's a chatbot that doesn't have any consequences for the world except somebody being frustrated, it's no big deal. If it's a AGI deciding about actions that could change the world drastically, this is a problem. I'm going to argue for Bayesian approaches. There's another issue which is connected to the reward maximization setup with the earlier, which is that through the training of our model, there's an optimization going on. And the thing we're optimizing could be wrong for several reasons. Maybe the reward function we're using isn't something that humans wrote themselves, or isn't really what they want. Maybe it's the result of training. So there's a mismatch between what they're optimizing and what we really want. And we maximize something, the AI maximizes something that is maybe slightly wrong. In general, the two things might be close to each other, but once you optimize, you can find the needle in the haystack. In other words, the place where the real thing we want and what it's optimizing are really very different, because that's where you can get a lot of reward. Just like the reward, taking control of the reward is not at all what we wanted, but it's a loophole in the way that we're setting things up. So yeah, so what can we do? In general, I'm going to argue that for safety, you want an agent that somehow knows about the different interpretations for what could go wrong. And I have this little toy setting here to explain this. Imagine you have an AI that is in front of two doors. So very simple, binary decision, go left or go right. And based on all the data that it has seen before, there are two theories that dominate in the sense that they're plausible with everything the AI has seen, and they're about as probable a posteriori. But they say different things about what you should do. So one theory, like the bubble on the left, says if you go left, there's going to be something really bad happening. People are going to die. You go right, you're going to get something good, cake. The other theory says, actually, if you go left, you're going to get cake. If you go right, nothing good, nothing bad. Okay, so raise your hand if you think we should go left. Good. If you think we should go right, yes. Even though we're not sure which one is correct. We don't toss a coin here to decide should we go left or right. But that's what maximum likelihood does. For reinforcement learning, it's going to pick one set of weights that is consistent with the data. Anything that is consistent with the data will have like minimal loss. So minimizing the fit to the data, maximizing the fit to the data or the reward function isn't good enough here from a safety perspective, because there could be one of the interpretations of the world under which this is very bad. And if you want to be safe, you want to think of safety as a constraint, then you need to look at all the theories that are compatible with the data and say, if one of them says this is very bad, I don't do it. Right? And we do that. Humans do that. And by the way, even if you had infinite amount of data, you would still have ambiguity about how the world works. And that comes out of the theory of causality. Unless you are able to experiment and intervene on everything in the world, which we can't, obviously, we can't move the sun, there's going to be ambiguity about what is the right explanation for things. So we have to deal with that uncertainty. And right now, our approaches in machine learning don't do that. Okay, so let me propose a path to get as good a guarantee as I can see right now, which seems also feasible in terms of machine learning. So I'm going to have a number of actors here. So this is probably the only slide with real equations. So what are the important components here of the discussion? We've got some notion of harm, and I'll come back. Like, how do we define that? Well, we can't define it formally in general. But let's say we express the kind of things that we don't want the AI to do in natural language. But now think of it as a random variable. We have actions. So we want to consider a particular action and ask the question if it's going to lead to harm, with what probability. Of course, the action is taken in some contexts, and the context, includes data D here. There is an assumption we're going to make that we're going to be kind of non-parametric, which just means that we're going to choose a family of explanations, like theories about the world, T here, that is basically infinitely large, so that it is almost certainly containing the right explanation, the correct explanation for how the world works. So think about the space of all programs, for example. Okay, so we're going to have, you can imagine a neural net that's going to generate a program or a theory or something, that humans can read. That is an explanation. It's going to be a very big program, but for now, let's assume we could do that. And there's an unknown program, an unknown theory, T star, that actually governs how things work in the world. We don't know what it is. But we know something about it. That's proposition 1, which is that as the amount of data increases under some reasonable assumptions, the correct theory will be among the dominating ones in the Bayesian posterior. In other words, the probability of the correct theory given the data, will be greater or equal or close to the probability for any theory, right? So that's good. So we don't know what T star is, but we know it has this property. And because of this property, we can prove the second proposition, in which we're going to introduce another theory, which we have more chances of finding. So it's the one defined on the top here, T, capital T. So it is the theory that maximizes this product. In other words, that has two parts. One is the Bayesian posterior. So it's a theory that is plausible. It's consistent with the data. So it has a high value under the Bayesian posterior over theories. And it is a theory that predicts something bad is going to happen. So P of harm, given the theory, is large. So we multiply these two things. So you have to have both. It's a plausible theory, and it says something bad is going to happen. And by the way, that corresponds essentially to the posterior probability of theory given the context and the data. Up to normalization, which doesn't matter in the argmax. So there's going to be an optimization problem at runtime, which we could amortize using neural nets, but there's an optimization problem at runtime for any given action that is proposed. We're going to have this guardrail that says, is there a theory that predicts something really bad is going to happen? And if we do find such a theory, then we don't take that action. We take the next one in line. Let's say you sort your actions by how useful they are according to some other, goals. So the proposition 2 says that the probability of harm under the correct theory is approximately less or equal to the probability of harm under this paranoid theory that we, that maximizes the posterior over theories that predict harm. So why is that interesting? Well, if we can, so there are two things we need to do here in order to get safety. We need to try to find this paranoid theory, capital T. And then we just check how much harm it predicts. And if it's above a threshold, we say don't do it. And so how do we get that theory T? We have to compute the Bayesian posterior over theories. And we have to do this maximization. So we have to search in the space of theories how to do that. How to, which one maximizes this product. The P of harm given the theory is something we have for free because the theory tells us about, how things would happen with what probability. That's what a theory does. Okay. So the outer loop of this is we have potentially two AI systems. I think it should be a single one, but anyways, think of them as two AI systems. Actually, two kinds of questions, right? One is proposing actions. For example, you could imagine you use your Bayesian posterior machinery to figure out actions that are desirable in the sense that, they should be chosen to achieve some desired outcome that, again, we could, write down in natural language. And as part of the things we want, also no harm. I mean, we should try to avoid that. The reason we can't just follow that Bayesian posterior is that, we could have 100 theories, let's say, that are plausible, and one of them says something bad is going to happen. When you look at the Bayesian posterior, it's a consensus over all these 100 theories, right? And so even though one of the members of the committee says something bad is going to happen, the consensus could be, fine, let's do it. Because the other theories in the committee say it's fine, right? And so we need the second step. Once we've considered an action, is the probability of harm, according to this worst case theory, less than a threshold? And I guess here it should be greater than threshold. So that's the high level picture. Now, how do we estimate all these things? And we have to do it efficiently, right? Because a priori, you might think that getting the Bayesian posterior over theories is intractable, and doing this maximization over theories is intractable. And you're right. So it's going to be approximations. So let's see first, how is that even possible to do with large neural nets? Because this is the technology that we have to really encapsulate powerful functions right now. And if we can reuse that, it'd be great. So these generative flow networks are an example of machine learning methods that, give us approaches to those goals. And let me say a few words about these G-flow nets. They are learning policies that take a sequence of actions such that these actions together yield some object, like a theory in our case. So here, theta stands for theory. Sorry, I changed letters. And so pi here is the policy we're going to be training. And we can define a loss function. I think I may have it later. I have some examples of loss functions later. We can define loss functions with the property that when we minimize that loss function, the sampler of theories will sample with probability proportional to some given reward function. So normally in RL, we look for a policy that maximizes the reward or the sum of rewards. Here, the goal is slightly different. It's to sample proportionally to the reward. So why would that be advantageous? Well, sampling versus maximizing is pretty much a difference between being Bayesian and just doing maximum likelihood. So if we choose the reward over theories to be in the bottom equation, sorry, I guess there were more equations than I thought. There's another one coming. If we do the prior times the likelihood as a reward, in other words, is this theory simple? Like, how many bits do I need to describe it? And is it consistent with the data? So that's the likelihood. So these are quantities we can compute. And there are ways to compute them more efficiently, so you don't actually need to look at the whole data set at a time, but it's a detail. Then the policy you get is going to sample proportionally to the posterior. So that's interesting. And we've been applying this in various small scale settings, like causal discovery, discovering causal explanations for data sets. It turns out you can also use the same kind of machinery both to sample from the posterior and to estimate the inference machinery, the things that answers questions. So if X is a question and Y is a candidate answer, we're looking for things like probability of Y given X, and of course the data, everything we've seen before. So the first job, sampling from the posterior, is intractable, but we can write it down. It's proportional to this product I said. The second job is intractable for a different reason, which is it requires, in principle, summing over all the theories. Each theory is going to propose an answer Y with some probability, but that theory is going to have a different posterior probability, and so you have to aggregate all of these products over all the theories. So both are intractable. But let me show you, more math. Wow. How am I doing with time?
We have about 10 minutes left, which doesn't include Q&A, but we can go an additional 10 minutes over.
All right. Okay, so I'm probably going to skip that, but yeah, if you go to the GFlowNet tutorial, which you can find by typing GFlowNet tutorial, you'll see that there's one of the tutorials about how you can both sample and marginalize, which explains these things. So in other words, the same GFlowNet machinery can allow you to both learn to sample and learn to sum over an intractable number of things if you were able to train the thing, in other words, to minimize its loss. And there are like tons of papers about this whole area there. Okay, let's kind of start wrapping up. one of the important properties that I find appealing here is that although we don't get hard guarantees because these conditional probabilities are going to be estimated by neural nets, we have a nice property, which is the more compute we have to make this neural net bigger and train it longer, the more we approach the correct probabilities, and thus we get, safer decisions. So that's cool. It would be better if we had hard guarantees, but I don't know how to get things like harm or what is right and wrong in a formal definition that you could do mathematical reasoning over. So dealing with probabilities and the uncertainty about even what it means, the thing we're trying to achieve, I think is a big plus here. But there are still a lot of challenges. So for example, yes, we're going to train these neural nets. Asymptotically, they might do the right thing with enough compute. But in practice, they're still going to make mistakes. How do we make sure that we account for these errors? And one possibility is to think of the errors made by the neural net as something you could estimate and then use that to create confidence intervals around the answers, the probabilities calculated by the neural nets, so that you can get a more conservative bound using that. Another issue is the problem of missing mode. So any computational method to estimate a distribution that is highly multimodal, like the Bayesian posterior, is almost guaranteed to have this weakness that it can't, in general, we can't be sure that it has discovered all the explanations, all the theories that explain the data. So one way to think about this concretely is science discovers theories. And every day some new theories that we hadn't thought about emerge that are consistent with the data. At any point, we can't be sure that we have covered all the theories that are consistent with the data. That's the problem of missing modes. So there's always going to be things that we didn't think about that could be true, and we need to deal with that. And one way to deal with that maybe is to say, okay, so we're going to reduce our guarantees to a weaker guarantee, which is, would a human who knows all the relevant theories that humans have put out, like in scientific papers, predict that something bad would happen with this action? So it's a lower bar, right? It's not, is this action bad in an absolute sense, but is it bad according to humans? And that's easier because now we can read all this. I mean, the AI can read all the scientific literature and consider all the theories that humans have tried as potential modes, potential explanations for things. And if it manages to cover all of these possibilities, which I think, GPT-4 is getting close to that, so it's not inconceivable at all, then we would have this sort of weaker guarantee that at least we don't do something that humans wouldn't want to do. All right. Another interesting aspect is, how are the theories going to be expressed? Ideally, they are like written in a language that humans can understand, like scientific papers. This would be useful in itself because that may contain advances in science. Also, it's a debugging tool. For the same reasons people are exploring interpretability in AI safety right now, it'd be good to know what are the beliefs, what are the theories, what are the explanations that this AI would form. And so the idea is to have two kinds of representations that the AI is going to be working with. One is like the natural language representation, and the other is something that's closer to a formal language, in which you can explicit reason, in which you can do like modus ponens, in which you can do probabilistic inference, without, and so one possibility is then, okay, so we have these two levels of representation, like what is actually going on in your thoughts and the words that come out of your mouth. And you want to make sure there is a mapping both ways, keep them consistent with each other, maybe using some kind of autoencoding loss. The last sort of open thing is, when we train this AI, we're going to do an optimization as well. And I was, said multiple times, optimizing something is potentially dangerous. So how do we make sure that we're not doing something bad while we are training the AI in the ways that I've been proposing? And I don't have the full answers to this, but my intuition is that if we, so first of all, yeah, if we make sure the criterion that is being optimized isn't optimizing through actions, and in fact, if we make sure there are no actions involved while we're training, no actions of the AI, coming from the AI itself, but rather observing things in the world, then I suspect we can get some guarantees, or some good reasons to think that we wouldn't have the problems that I've talked about before. Right. So that's it. I'm recruiting. If you want to learn more, you can check my latest blog posts, which talks about this research program. The keynote I gave at the New Orleans Alignment Workshop is sort of an older version of this talk. And if you want to help in any way, reach out to me. Thanks.
Thank you so much. So we have about 10 minutes for questions. And as a reminder, we're going to pass the mic to you. Please raise your hand. Try to keep the mic close to your mouth. And please try to ask all long-winded comments, at least in the form of a question. Try to aim for that. So I saw your hand first.
Hello. Thank you for your presentation. My understanding is that the kind of problems with the tutors only happens when you are not within the training distribution, and that if you train an RL agent to face many such problems, and you sample the new one from the same distribution, it would choose the right door. So I feel like the GFLNet is trying to answer a question about generalization.
Why would it? I don't understand.
Because it gets like lower reward on average, and empirically agents are good at maximizing reward.
Right, but it only has one life experience, and both theories are compatible with the data. So I don't think what you say is going to work.
I'd be surprised if okay.
I mean, there is uncertainty for sure about what is the right thing to do or the right interpretation. And I don't see how you can avoid capturing that in a way that's going to be safe. But yeah.
Thank you for the,
Maybe there is, I just don't see it.
yes, thank you for the excellent talk. Do you see any current approaches in formal methods to give provable guarantees that you find particularly compelling?
I don't, but we definitely need to do it, because if we can, we're going to get stronger guarantees than what I'm talking about. So in general, I think, at the level of humanity, we should investigate the different levels of risk reward here, right? So the optimal thing is to have a hard guarantee that the AI is not going to turn against humans. But maybe this is not achievable. So you can think of what I'm talking about as like one lower down, one level down in guarantees by being probabilistic, essentially, and using learning to estimate those probabilities. And you can have weaker things, like many of the things we're doing now. And we need to do all of those things because we don't know what is actually going to work.
Is it on? Oh, yeah. Thanks for the talk. Similar question to the last one. So this talk is based on the idea that you have these theories. You say these theories should be expressed simultaneously, or sort of cast between natural language and a formal language.
Yes.
And I'm interested in, first, what are the leading candidates for a formal language? It sounds like maybe, there's still a lot of work to be done. If there's no sort of obvious leading candidate, what are the properties that you're looking for? It sounds like you're looking for something composable, so you can do partial theory, something evolvable. So
Thanks. This is a great question. So I've written more about it in my blog post. But the way I think about, and it's something that I think requires a lot more attention and research. But my current path aims at theories that are made of statements. What is a statement is something that can be true or false. So it's really close to formal language. And that in principle, you can reason to check the coherence of these statements with each other directly without, I mean, you could use other statements, but basically things like modus or probabilistic inference is just pure math that tells you how to combine these statements and check their mutual coherence. So these statements, you can understand them as short sentences that say something about the world. And of course, they could relate to other statements. Like in a statement, you could define things and then use that in another statement, for example, just like we do in math. Right? So basically, you can think of that language close to math, but something translatable to natural language because it talks about the world, not just about mathematical concepts.
Thanks very much for Thanks very much for the talk. I guess one general weakness of this Bayesian inference formalism is that if the model's misspecified, the whole thing might fall apart. You might not have the correct theory supported. One way you can misspecify, which I didn't really talk about, is the likelihood. How likely are you to observe the data given the theory? Like you talked about, like how to specify. I think it's easy to misspecify. Like you might, I don't know, assume too little noise or something like that, or like.
No, you don't need. So I said at the beginning we're going to be non-parametric. So what that means, for example, is concretely that think of the theories not as something finite size, but it could be any length. And we know, like, by basic arguments in computer science, that pretty much everything can be represented in this way, like, with a Turing equivalence. So every theory can be represented with a program, basically.
I mean, I guess I could agree with that. That's specifying like the space of priors, but this is like how likely are you to observe a data given the particular hypothesis. Right?
A member of the family of theories is a likelihood function, directly or indirectly. Right? It tells you how to make sense, how to predict that something will happen given other things. So the likelihood function is the theory. Once you specify the theory, it's just simple calculations that tell you how to predict things. So a theory also includes latent variables about specific interpretations for things you have observed. So in a theory, really, you have like what you would normally think of a theory as like how things work in the world, and you have explanations for specific things. And of course, when you specify both of these things, this is the likelihood function. Like basically how things work is something like maybe a neural net that calculates the likelihood of some piece of data given some latent variables, for example.
I actually want to come back to the non-parametric Bayesian statistics.
Yeah.
Right? So in practice, we're using parameterized model classes.
That's right. But actually not, because we are allowing our neural nets to be as big as we can.
Yeah, but I mean, we know that introducing a parameter function map introduces inductive biases towards certain kinds of models.
Sure.
Models
but having inductive biases still allows you to be non-parametric.
Yeah, but this could, I think this could violate some of these bounds if the inductive
So long
bias
as the
is sufficient.
support is full, then you're good. Now, it may be that if we choose the wrong inductive biases, and these are soft, I'm talking about soft inductive biases, right? So if we choose the wrong ones, it could be that we need more data to counter the wrongness of the prior. So good inductive biases will allow us to generalize better, but bad inductive biases, so long as they're still soft, like they still give full support to any theory, still allow the posterior to contain the true answer.
You could be very far away from this.
Then you need more data in order to make the correct theory rise up in the posterior.
But the model doesn't look like a collection of Gaussians.
No. I'm not talking about Gaussians. Talking about, like, think of theories like scientific papers. The whole scientific literature is not one theory, actually, because there are different papers that say contradictory things. That's good because there are multiple theories. But think of it in that form.
I'm gonna follow up.
Sure, please.
So it sounds like you need two properties of theories. You need both that they're sufficiently interpretable that we can determine whether or not they imply harm in a given action. And we also need the property that we can measure their likelihood and they need to be very predictive.
Yes.
These seem like extremely hard properties to both have naively. Like for
Yes,
example,
yes.
if you have a stream of data that is
Yeah, I understand the
next
question.
tokens,
Yeah, I understand the question.
what type of theory can you use to have that?
Yes, that's a great one. Again, I'm going to give you the answer I currently think about, but this is the sort of thing that requires a lot more work. But just to give a sense that I think it's not impossible to resolve this. First, think about, again, going back to how humans do it. We're not able in natural language to have full descriptions of what we know, right? There's a lot that is hidden in some neural net that we can't communicate. But the more we can put in sort of a natural language form, the better. And I'm going to use physics as a sort of example in chemistry. So you could just have a theory that's like quantum physics, but with finite computational resources, you can't predict much with it. So you could have a big neural net that approximates quantum physics, so that you can answer more questions than the simple ones you would do otherwise. But there are better solutions if you can find them, like DFT in chemistry. Right? So it's an approximation to the quantum physics, but it can be applied in places where the quantum physics practically cannot be applied because we have finite computational resources. And even if we use DFT, it may be too expensive in some cases. And so people currently train neural nets to approximate the DFT. So things are, getting more subtle here, right? So you in general, you're going to have a mix of things that are symbolically expressed and things that are not, like continuous parameters of some machinery, right? And the Bayesian posterior, if we're able to like do the fishing of good modes, is going to look for the symbolic stuff. It's going to try to put as much of its knowledge into a form that's compact, because that's the thing that's going to generalize better. Does that make sense to you?
Makes sense. I don't think it fully answers my question, but
So one way to think about it practically is you have a neural net that can spit out symbols or statements and also spit out vectors. Right? And of course, the vectors may have names, and then the symbols can refer to those names to say, well, this is what you should use in this particular likelihood function or whatever.
Thank you so much, everyone, for your questions. And please, one more round of applause for Yoshua Bengio.